case of optimization, we're going to be finding a maximum instead of a minimum, which is just what we found. We just saw the video where we folded the sides up on a box which had the corners cut out. And this is exactly what I've drawn here, the dotted lines being the areas where the corners were cut out, and these lines noting that x is the same on every single side of these squares because they're all equal squares. So we have the box, which is 12 inches by 10 inches, and we also have the diagram of what it looks like when it's folded up. So you'll notice here that I have 10 minus 2x as one of the sides. This is because this side here is 10, but there's also an x here and an x here, and when you fold it up, those x's kind of disappear. So we have to take out those x's in order to find how long the side is, and that's why we have 10 minus 2x, and it's the same thing for 12 minus 2x. The height of the box is x, because when you fold up the side, this little x region becomes the vertical component, and that's the height. So I've written out the components of our diagram here. We have the length as 10 minus 2x, the width as 12 minus 2x, and the height as x. And I also have our equation for volume, because we're trying to find the greatest volume for the box. So the equation for volume is L times W times H, and now we can simply plug in the numbers in this formula to get out what V actually equals. So the volume for our box is equal to 4x times x squared minus 11x plus 30. I simply just multiplied these together in order to create a polynomial here. It makes it simpler so that we don't have to do a bunch of product laws later when we have to find the derivative. And I thought this was important to mention because in all the other questions we were doing, we didn't really talk about restrictions and how those worked. Like when we did the last question with the garden fence, we found that the length of the side couldn't be less than 0, and that was a restriction. We just didn't write it out. In this case, I just wanted to make it clear that all dimensions must be positive. And that means that this can't be 0, this whole side can't be 0, and this whole side can't be 0. So I wrote a little bit of a statement here. X must be greater than 0. 6 minus x has to be greater than 0, and 5 minus x has to be greater than 0 in order for our dimensions to function. So now that we have our function for b, we need to get the derivative. And our derivative, once simplified, is 3x squared minus 22x plus 30. I figured I wouldn't write it all up here or else we wouldn't have room on the board, and I also want you guys to be able to figure it out on your own on your pieces of paper. When I figured this out, you can see my little bit of work here where I did the housekeeping and the f and f prime, but that's, once again, I want you guys to be able to figure out yourself. I just gave you a little bit of a hint. Now we need to move on to our critical values. F prime of x equal to 0, so I set it equal to 0, except this one you can't factor it normally, so you have to use the quadratic formula, which is 22 plus or minus the square root of negative 22 squared. Remember to keep that negative inside parentheses or else it's going to square it and turn into a negative, and if you have a negative there, the entire function doesn't work because there's a negative under a square root. So it's that negative 22 squared minus 4 times 3 times 30 divided by 2 times 3. Once you figure this out, you'll see that I have that x over there, and I'll explain in a second here, but we have our two values for the plus and minus, which is 5.523 and 1.811. I just didn't write the positive and negative ones because I want you guys to remember that if you can't figure it out using exact values, you just round to 3 decimal places. So now the reason why I had to cross this one out is because if we look back at our restrictions, we see that 5 minus x has to be greater than 0 in order for that side to work. But now that we plug it into there, 5 minus that 5.523 will end up being a negative number, and that negative number can't be a length, so that one is immediately crossed out. The 1.811, it works for all dimensions, so we can move that on for our sign analysis. In our sign analysis, I put the 1.811 right in the center there, and it's negative infinity to positive infinity, which is actually incorrect because we want it to be greater than 0, so it can't actually be up to negative infinity. But we have the positive, negative. We know we're trying to find a maximum, so when you're plugging it in, if you got a negative then a positive, then you probably did something wrong in your sign analysis, or earlier in your derivative you did something wrong. So I plugged in 0 here, and it worked just fine, I got a positive number, and I plugged in 2 here, and I got a negative number, and that just means that we have our maximum, because f prime is greater than 0 turns into f prime is smaller than 0. That's how we know our max is at 1.811. Using that, we can write our final statement, and we know that the value of x that produces the greatest volume for the box is 1.811 inches. I've shown you 2 cases of optimization, and I put another question in your notes for you guys to figure it out. So I want you guys to solve that for me, and I'll come help you out if you need it.
How about we just opt out of optimization and leave this place?
Yes, Emily?
Can I go to the bathroom?
Ah, whatever.
Stupid.
We're doing something called related rates. It seemed kind of daunting at first, but it's once again using our derivatives. And the related rates is basically a distance, an area, or volume in terms of time. So our derivatives are going to be d blank over dt because everything is going to be related to time and in terms of time.
What you're talking about is the amount of grapes I can fit in my mouth in 1 minute. If you're wondering, it's 36.
Our first example of related rates is the video that we just saw with the cone filling up with water under the sink. I drew a picture of the cone here, and you'll notice I separated this cone into two right-angled triangles. The relationship with the radius and the height actually makes a perfect right-angled triangle with the center of our circle at the top of the cone. And this can be separated into two, and I'll tell you why now. So the height of the new water is 18 inches, and the radius from the top is 4 inches. But we also know that it started at 5 inches when we started pouring in the water, and we just need to know that the radius originally at the bottom here. So we can set up a ratio using these numbers in order to find what little r is. So we plug in all of our numbers. So we have 4 over 16 for our radius height ratio for the new one, and for our old one, we just have 5, and with that we can see that 1/4 of 5 is 1.25, and that's what our new radius is, 1.25 inches. We also have our change in volume over time, which is 4 inches cubed per minute. Now you'll see that I set up another ratio here where I wrote r in terms of h, the other way around, h in terms of r, and that's important for later actually when we start doing our derivatives. So in order to find what the change in radius is over time, which is what the question is asking, we need to find the derivative of the volume. The formula for volume is 1/3 pi r squared times h. Unfortunately, we can't just use this formula directly because when we find the derivative, we're going to have the derivative of h, which is dh dt. And we have no indication of h in terms of time, so we need to remedy this by looking back at our ratios. I turned 4 over 16 into 1/4. It makes it simpler for our calculations later. Instead of plugging in h that we have right here, the 5 inches, we're actually just going to replace h by isolating for it and finding out that h is the same thing as 4 times the radius. We can plug in 4r for h in the formula, and now our new formula is b 1/3 pi r squared times 4r. We can simplify this even further by seeing that the volume is the same thing as 4/3 pi r cubed. I just multiplied the 4 over to the 1/3 and the r by the r squared. Now we can find the derivative of this, and it was important to simplify because now we don't have to do a product law. We can just simply do a power because pi is a number, not a variable. So now I took the 3 and multiplied by our 4/3, and the 3 canceled out, so we just have 4 pi r squared times dr dt. We found the derivative, which means we need to replace every derivative with d, its variable, in terms of time. It's kind of like implicit differentiation, how you have to put dy dx. It's the same sort of deal, as you'll see our volume is dv dt, because our volume is in terms of time. Now we can plug in the r that we found, which is 1.25, our dv dt, which is 4, and we can rearrange and find dr dt. So once you rearrange this, you find that the derivative of r in terms of time is 0.204. Once you have that value, you can do the final statement just like we have been with other questions in optimization, which is that the change in radius of the water over time is 0.204 inches per minute.